Yeah, I was going to ask you. He read my mind.
Before we get started, I want to remind all of you the basis for numerical differentiation. Why is it not coming on? Okay. And that is that we can approximate the partial of a function with respect to the variable as the function where everything is at the point of calculation. Okay, at the nominal steady state here, with one exception. The only variable that will not be at the nominal steady state is the variable at which we are taking the partial of. So in this case, xj. So I'll write it here shorthand, but there's also a purpose for that. So the x vector, everything will be a nominal except for the jth component. So I'll write here x equals x naught except xj will be xj naught plus delta xj. All other variables nominal steady state, so u at u naught, d at d naught, minus the function where everything is at nominal, divided by delta xj. And the heuristic we're using, I have never seen it fail. Heuristic for double precision, and you want to have the highest precision you can have. Choose delta xj to be 10 to the minus 8 times absolute value of xj naught. 10 to the minus 7 also works. In the case where I don't think ever happens in reality, that's if xj naught is different than 0. If it's equal to 0, take something small. I would try 10 to the minus 8, for example, something like that. Clear, everyone? Any questions here?
Shouldn't you like the limit constant to x approximation?
No.
Why?
Limit is the exact definition. This is my approximation. This is how I calculate it. Anybody else? Clear, everyone?
Could you turn on the blackboard light? Or is it off one?
Well, okay, but that's all I wanted to say. I'll turn it off for a second, but it's hard to see this screen when I turn the blackboard light.
Okay, sorry.
All right, Mika. Okay, I'll give you a couple of minutes with the board before we get started.
So what does that mean?
What do you mean?
What is that?
What do you mean, what is it? What is what?
What is that? I don't know. I don't know what you just wrote. I was copying it down.
Well, it's not new stuff. It's
Yeah,
the
but-
important thing that we were
Yeah, you
doing
said-
last time.
you said
is
the only
how
thing-
we are going to be calculating AIJ. AIJ, which is, as we have seen, the partial of a phi with respect to its jet nominal steady state. Okay? We can approximate it like that. And as I mentioned last time, the error of this approximation is large for very big delta xj, and goes down, there's a sweet spot, and then it increases again and levels off whatever is the error when you take the result as 0. Because for very small delta xj, as we saw last time, the result is 0. So I'm telling you this sweet spot is going to be around 10 to the minus 8 xg naught, where the error is really tiny. Okay? All right, so let's return now to the program. Let me remind you what we have been doing. So far, we have learned, if we are not familiar with VBA, how we define functions. So, first, we declare some global variables. The private command declares variables are going to be shared by the functions and the subroutines. Yes?
I don't understand why you put, like, where'd you get the 100 and the 20 from? Because in the example you did.
Well, you were here last time, right?
Yeah.
How about if you see me after class? Because I already said all that last time.
Okay.
So, ask questions on the new stuff, but guys, I have to put a limit on repeats of previous lectures. I don't want to discourage your questions, okay? But I cannot repeat all previous lectures.
Okay.
So if something was not clear in the lecture, come and see me after lecture. But
Got it.
make sure you understand the lecture before you go to the next lecture.
Yeah,
because
yeah,
I
it's
can't
like-
afford to take
it's
the
like
time
everything I don't-
to repeat everything I have done before.
Okay, got it.
Okay.
Sorry.
No, it's all right. I don't want to discourage you. By all means, please ask questions today.
Okay.
But I have to put a limit to questions from past material.
Okay.
All right. So, but anyway, I'll try again to answer that. We dimension the system to save space for much larger systems than the two equations we have here. So, with the dimension I've given, this program can be used for up to 100 equations for 100 variables. For state variables and for 20 disturbances, that's why I took 20 as the size I put for disturbances. Usually you won't have that many disturbances, but state variables you can have quite a few. Okay? And so we define the f function. The arguments, and in the argument you bring the entire vector. So when I have argument x, that's the entire vector x. Use, of course, the scalar. D is the entire vector D. And I need an I because the function is a scalar function and returns the ith component. And so this is our example. This is f1. So if I equals 1, f is going to be returned as f1. So if you call that function with I equals 1, you get back f1. If you call that function with I2, you get f2. And if you call it with anything else, you have a problem, and that allows you to it. The second function is just a scalar function. That's the measurement function. So there is no I, there's no component there, and only depends on the delayed state variable. Okay? Here's the general x. Whatever I call it x with, that's what we'll calculate. And then we started the main program. At the beginning, we specified how many state variables we have. N is the number of state variables. Might work for the moment. Remember, an apostrophe, and you can put it anywhere in line, is explanatory remarks that don't affect code execution. So this is the number of state variables. And then R is the number of disturbances. And we talked about how we interface between Excel and VBA. One way you can do it is with the range command. But the range command has some disadvantages. You cannot easily automatically change variables. You can do that with the cells command. We call it differently in the range and the cells command. In the range command, we have standard Excel notation, which has column first, row second. In the cells command, we have standard matrix notation, which has row first, column second. So B3 range is cells 3, 2. Okay? So the first thing we did was to read the nominal values. So even though in this case it's 3 lines instead of 2 lines to do it like that, I'm writing a program that is general, and if I have 20 state variables, it's a lot more efficient to have 3 lines. If I had 20, it's exactly the same code. While if I did it each one individually, I would have to type 20 statements. So this is the power of looping. And the nominal steady state of the manipulated input and the nominal steady state of the disturbances. Okay, so that's where we stopped last time. We're ready now to actually do the work, and the very first thing is to calculate our A matrix. We need to have an efficient way to calculate all the components of the of the A matrix. If I had 100 state variables, that's 100 by 100 components. Okay? What's the efficient way of doing that? To use a loop, and in this case actually a double loop. I have 2 arguments. I want to go from I 1 to n and j 1 to n. So we'll do a double loop, and 4 statements is one way to loop in VBA. We have used it before. So to calculate the A matrix, it's good to indent. Is this big enough for you guys to be seeing? There is a way I can make it larger. I always forget how to do it.
Under tools and options. Second tab.
Yeah, thank you. Yeah. That's it. John, is this big enough to read comfortably?
Oh, yeah, that's right.
All right. So it's always a good idea to indent and to align the closing statement with what you have. So now 4 and x should be at the same level and everything inside indented. So my outer loop will be for I equals 1 to n. My inner loop for j equals 1 to n in this case. Here we'll have the calculation of Aij, although as we will see in a minute, we'll have and so here we'll calculate Aij, and after we calculate Aij, we need to close the loops. You close first the inner loop, So next j, and you go close next the outer loop. Okay, so I guess I'll turn off the light to explain. How am I going to calculate a and j? Well, I'll use this formula. I have already defined the function f. This is easy. I will replace x in the argument by x naught, u in the argument by u naught, d in the argument by d naught. You understand? When I have a function and I'm calling it with argument something, whatever I put in the argument and I'm calling it, that's what it will calculate. Now if we look at the left thing, there's a purpose I wrote it as x naught except for the jth component. The easy way to calculate it, to create this, is to first, I will call this, let me give it a name. Let's see, COT students. Do we remember what name I called it in COT? Anybody? Oh, yes. I called it X special. Very good, though. And Christian almost there. Okay, so we want the X, and everything is nominal except for the jth component. What's an easy way to create it? First set that X special equal to X nominal steady state, and then change the jth component to produce. Okay? But that would require also we must have dxj. So I guess we can do it without defining it. Well, might make it clear. So, and obviously you see here that I have some extra variables that we have to declare, but so the first thing, let's define the dxj.
You turn off the light.
For that procedure, you're supposed to use d instead of e, but I don't haven't seen ever having any difference. So this is equivalent to 1e minus a, 10 to the minus a, times the absolute value of x naught jth component. That sets dxj according to that heuristic. Just in case that we have somehow a case where the nominal value is 0, to protect ourselves against that, we can put a little if statement. And we have used if before, and we had the statement if, commands, and if. But if you put it all in one line, you don't need to put an and if. So an alternative that can only be used for short commands is to use if dxj not equal to 0, then I'm going to correct that and make it equals, let's say, something small. Now let's make it nice so it's not the same.